I'd like to be able to drive smoothly in town, even though the streets are full of signal lights and stop-and-go traffic. It would be nice to have more power when passing at high speeds or to climb a steep hill. It's nice to have power, but I don't want a gas guzzler. I'd like to be able to economize on fuel. As a member of society, I don't want to spew harmful exhaust gases all over. I want a car to be environmentally friendly. Up until now, we at Toyota have been addressing these needs of customers and society through various technologies. Now, a new type of engine control system which achieves high power, low fuel consumption, and cleaner exhaust gases at high levels has been born. It is Vvt I, or Variable Valve Timing Intelligent. The Vvt I engine offers superb overall performance. To find out what this performance is about, let's compare the new LS400 equipped with the 1UZ FE engine with the previous model. With an engine modification that consists primarily of the adoption of the Vvt I system, the new LS400 exhibits an improvement of over 10% in terms of output and torque. In addition, fuel economy based on average street driving has improved 6%, and the nitrogen oxides in the exhaust gases has decreased 40%. Ordinarily, a higher output, better fuel economy, and cleaner exhaust gases cannot be achieved simultaneously by the engine alone. However, as this data indicates, the Vvt I engine has successfully satisfied these seemingly conflicting demands. Now, let's observe how the Vvt I system accomplishes these feats. Here's a cutaway of an ordinary engine. Since the cutaway cannot be used to simulate the process of combustion, let's observe a demonstration through computer-generated graphics. First, the intake valve opens. The piston descends, and the air-fuel mixture is drawn into the cylinder. Then the intake valve closes. And the piston ascends to compress the air-fuel mixture. The spark plug ignites it. The air-fuel mixture quickly burns and the pressure inside the cylinder increases, pushing the piston down. This movement is converted into engine output. The exhaust valve opens and the piston ascends. The exhaust gases, the result of combustion, are discharged from the cylinder. As we have learned from the processes described so far, the engine burns the air-fuel mixture to generate power. The timing in which the valves open and close in order to draw in the air-fuel mixture and to discharge the exhaust gases is called valve timing. Now, let's examine the actual valve timing. This is slightly different from what we saw earlier. In an actual engine, the intake valve opens slightly while the piston is discharging the exhaust before it reaches its topmost position, which is called top dead center, or TDC. And the intake valve closes at the beginning of the compression stroke, after the piston passes its bottommost position, which is bottom dead center, or BDC. Meanwhile, the exhaust valve opens during combustion before the piston reaches its bottom dead center, and closes past the top dead center after the intake stroke begins. Let's find out why, in an actual engine, the valve doesn't open and close when the piston is at its top dead center or bottom dead center. When the piston starts to descend, a vacuum is created in the cylinder so that the pressure in the cylinder becomes lower than the pressure in the intake port. At this time, when the intake valve opens, the air-fuel mixture in the intake port is drawn into the cylinder. However, even if the intake valve is opened, the air-fuel mixture that was standing by in the intake port until that time cannot move immediately. Consequently, the drawing of the air-fuel mixture from the intake port into the cylinder is slightly delayed in relation to the movement of the piston, a phenomenon known as intake lag. To compensate for this intake lag, the intake valve of an actual engine is designed to open before the piston reaches its top dead center. Due to the intake lag, even after the piston reverses at bottom dead center and begins its ascent, the pressure in the cylinder for some time remains lower than that of the intake port. Until this difference in pressure is eliminated by the further ascension of the piston, the air-fuel mixture continues to be drawn into the cylinder. Consequently, to draw in as much air-fuel mixture as possible, engines are designed so that the intake valve closes after the piston moves past bottom dead center, after the compression stroke has begun. However, when engine RPM is low, the piston moves at a slow speed and the intake lag is minimal. Therefore, there is no need for the intake valve to open before top dead center or to close past bottom dead center. If the intake valve opens before top dead center, it could have the bad effect of drawing in exhaust gases and the detrimental effect of causing the engine to discharge the air-fuel mixture that was drawn in if the intake valve closes past bottom dead center. On the other hand, if engine RPM is high, the intake resistance increases. Then the intake cannot catch up with the faster piston speed, creating a larger intake lag. To make up for the intake lag, the faster the engine RPM, the earlier the intake valve must open before top dead center, and the later it must close past bottom dead center. However, in conventional engines, the valve timing is fixed and cannot be changed. It would be ideal to enable valve timing to optimally accommodate engine conditions that constantly change. The answer to this is the Vvt I system. Vvt I is a system that varies the timing of the intake valves to achieve optimal valve timing. This shows that the cam position has moved and that the timing of the opening and closing of the valves has changed. Let's observe how this mechanism works. The vertical movement of the pistons is converted into rotational movement of the crankshaft. This rotational movement is transmitted by the timing belt via the pulley to the camshaft. Then the camshafts rotate to open and close the valves. In an engine in which the pulley and camshaft rotate in unison, the timing to open and close the intake valves is constant in relation to the position of the piston and cannot be changed. However, in the Vvt I system, the camshaft for the intake valves shifts continuously in relation to its pulley. Accordingly, Vvt I varies the timing to open and close the intake valves constantly to an optimal level by taking engine RPM and load into consideration. Let's now find out how Vvt I changes the valve timing and under what engine conditions it operates. First, let's observe the engine at idle. During idling, the engine does not need to generate power to run the vehicle. The only performance that's demanded of the engine is to idle smoothly without any vibrations. As we saw earlier, the engine RPM is low and the piston speed is low during idle. Therefore, there is no need to open the intake valve early on. Moreover, because the throttle valve is closed, the amount of intake is minimal and the pressure in the intake port is low. That is to say, the vacuum in the intake port is high. The condition in which the intake and exhaust valves are open simultaneously, as illustrated here, is called valve overlap. In this condition, the high-pressure exhaust gases enter the low-pressure intake port. When the air-fuel mixture is in this state, combustion becomes unstable, causing the engine RPM to also become unstable. For these reasons, in conventional engines that cannot avoid valve overlap because the valve timing is fixed, it becomes necessary to raise the RPM at idle to a certain extent in order to stabilize the engine RPM. On the other hand, Vvt I retards the opening timing of the intake valve during idling until there is no valve overlap. Thus, the air-fuel mixture that is drawn in is in a favorable state without any exhaust gas contamination. The combustion becomes stable, resulting in stable engine RPM. As a result, engine idle is stabilized even when the engine RPM is lowered. The engine's fuel economy increases in relation to the amount of RPM that was reduced. Next, let's observe the vehicle during normal driving. Normal driving is a condition of the vehicle during which the accelerator pedal is partially depressed. Operations that do not put a large load on the engine, such as constant speed operation, ordinary acceleration, and ascending a mild slope, are also considered normal driving. Under such conditions, a Vvt I advances the valve timing to increase the overlap. The overlap is now utilized effectively, although it had a bad effect during idling, which we mentioned earlier. Let's find out how this is made possible. As we learned earlier during the explanation of idling, valve overlap causes the high-pressure exhaust gas to enter the intake port, creating a situation that is unfavorable for the air-fuel mixture. However, at this time, because the RPM is relatively higher, the engine RPM does not become unstable. Moreover, because there's no need to generate a large output during normal driving, there's plenty of power left in terms of the engine's potential. By increasing the valve overlap and leading the exhaust gases to enter the intake port, the vacuum in the intake port is reduced by the high-pressure exhaust gases. For this reason, during the intake stroke, in which the air-fuel mixture is drawn in, the resistance that is present when the piston descends is reduced. In other words, the force of the vacuum pressure that attempts to pull the piston upward is reduced. As a result, fuel economy is increased. Introducing the exhaust gases into the intake port has another important significance. It makes the exhaust gases cleaner. First of all, the unburned fuel, which is present in the exhaust gases in the form of hydrocarbons, is introduced again into the intake. By re-burning it in this manner, the amount of hydrocarbons is reduced. Moreover, the combustion temperature can be reduced by introducing unburnable exhaust gases into the intake. As a result, the generation of nitrogen oxides, which are a cause of photochemical smog, can be minimized. Thus, Vvt I advances the valve timing during normal driving conditions when the engine has plenty of power to spare. By doing so, the desired level of driving performance can be provided, fuel economy is improved, and exhaust gases are made cleaner. The third condition is a high load condition in which the accelerator pedal is pressed all the way, such as when passing at high speeds or climbing a steep slope. In such conditions, a large output is demanded of the engine. At this time, Vvt I advances the valve timing. From the perspective of valve timing alone, the condition appears the same as that of normal driving conditions discussed earlier. However, the objective is different. When the driver is about to depress the accelerator pedal all the way, the engine RPM is still low and the piston is operating at a low speed, so the intake lag of the air-fuel mixture is short. Under such conditions, if the timing at which the valve is closed is delayed, the air-fuel mixture gets pushed back into the intake port. As a result, the amount of air-fuel mixture that can be burned is reduced. Therefore, in order to draw in the maximum amount of air-fuel mixture without pushback, the valve must be closed early on by advancing the valve timing. For this reason, the timing at which the valve opens is also advanced, creating a larger valve overlap. Because the throttle valve is open wide, the pressure in the intake port is closer to atmospheric pressure with a minimal amount of vacuum. Therefore, the amount of backflow of the exhaust gases into the intake port is kept smaller than that of normal driving. When the driver continues to press on the accelerator pedal, the engine RPM rises and the intake lag becomes greater. At this time, Vvt I gradually retards the valve timing to accommodate the intake lag so that an even greater amount of air-fuel mixture can be drawn in. When the accelerator pedal is pressed all the way like this, Vvt I causes as much air-fuel mixture as possible to be drawn into the cylinder to maximize the potential of the engine. As described so far, Vvt I controls the valve timing to bring the optimal engine performance into full play under the various driving conditions that are normally encountered. As a result, in addition to generating a high output when needed, Vvt I greatly contributes to increased fuel economy and cleaner exhaust gases. Next, let's observe the mechanism of Vvt I control. This control is performed electronically. First of all, to find the cam angle in relation to the piston position, a crankshaft position sensor, and a camshaft position sensor are used. To find the engine load, an airflow meter, and a throttle position sensor are used. The signal from the water temperature sensor detects the warm-up condition of the engine. The information that's provided by these sensors enables the ECU to calculate the optimal timing for the intake valve. Then the ECU sends a signal to the oil control valve, or OCV. The oil control valve switches the hydraulic pressure that is applied to the Vvt I pulley. As described earlier, the portion that is driven by the timing belt and the camshaft portion are not fixed to each other, and their phases shift through hydraulic pressure. In this manner, the timing of the intake valve changes continuously. Let's observe how control is performed. The ECU uses 3 types of signals to control valve timing. The first example is that of advancing the valve timing. The ECU outputs an advanced timing signal to the oil control valve to switch the oil passage. Then hydraulic pressure is applied to the piston that is located on the Vvt I pulley, causing the camshaft to rotate in the advanced direction. When the optimal valve timing is reached, the ECU outputs a signal to secure the timing and shuts off the oil passage. Then the camshaft becomes secured at that angle. When the engine condition changes and the valve timing must be retarded, the ECU outputs a retard timing signal and switches the oil passage to reverse the oil flow. Then hydraulic pressure is applied to the pulley on the opposite side of the piston, causing the camshaft to rotate in the retard direction. Through such control, Vvt I continuously changes the valve timing. The Vvt I system enabled torque, fuel economy, and cleaner exhaust gases at high levels. It's an ideal performance that one could only dream of with the previous fixed valve timing engine. Vvt I is cutting-edge technology in which the overall performance of the engine has been improved. The Vvt I control system is equipped with a self-diagnosis function. This function enables the detection of any malfunction in the Vvt I systems, sensors, or in the signals that are output to the oil control valve, or OCV. If a malfunction occurs in the Vvt I system, the check engine light in the combination meter turns on to alert the driver of the malfunction. Even if a malfunction is not shown via the check engine light, the engine ECU stores the trouble code in the form of a diagnostic trouble code, or DTC, which provides the same function as that of the light. The DTC can be accessed by connecting a handheld tester to the DLC3 connector. To access the DTC without using a handheld tester, use the following procedure. First, use the SST to connect terminals 13 and 4 in the DLC3 connector. Next, turn the ignition switch on. Then the check engine light flashes to output the DTC. At this time, if the light outputs code 59, there's a malfunction in the system. In this case, perform troubleshooting as follows. First, check the engine's valve timing. Bring the piston in the number 1 cylinder to top dead center of the compression stroke. Then, check the aligning marks to verify that the camshaft timing pulley is in the correct position. If the marks do not line up, adjust the valve timing. If the marks line up properly, move on to the process for checking the OCV operation. Check the OCV operation in the following manner. First, start the engine and allow it to warm up. Next, connect the handheld tester. Using the Active Test menu, turn the OCV on and off and check the engine speed. If the engine operates normally when the OCV is off, and if the idle RPM becomes unstable or the engine stalls when the OCV is on, the Vvt I system is operating normally. Therefore, you must look for causes other than the Vvt I. If the OCV operates improperly, check the engine ECU. Connect the oscilloscope to terminals OCV plus and OCV minus and increase the engine RPM to verify that the width of the waveform becomes shorter. If the waveform is normal, refer to the repair manual for inspecting the Vvt I controller assembly's OCV and the oil passage. If the waveform is abnormal, the engine ECU must be inspected or replaced. The inspection procedures without using a handheld tester are given in the repair manual for the appropriate model. Here are some additional service reminders that you should keep in mind. First, this is the valve timing if the OCV is open or short-circuited, or if there's an oil leakage due to a damaged O-ring. In this case, the OCV does not move and the valve timing is fixed at the most retarded timing. Therefore, even if you press the accelerator all the way, the engine will not be able to output the proper amount of power. Furthermore, the valve timing will remain at the most retarded timing even when the engine is turned off or during starting. Thus, by eliminating valve overlap and preventing the exhaust gases from re-entering the intake port, the engine's starting performance is improved. The methods for replacing the timing belt and for aligning the valve timing are the same as that of the previous model. Last, as a service reminder, never remove these bolts. The timing pulley must not be disassembled. These bolts are used for adjusting the backlash of the spline gear, which is adjusted and assembled precisely at the factory. If the backlash is altered, it could create an abnormal noise or grind the gears. Therefore, if you ever disassemble the timing pulley, you will not be able to readjust it properly. Then the pulley must be replaced as an assembly. For detailed inspection procedures, refer to the repair manual.